Yeah. Then we can just wait. You know what? Like,
Yeah, we can switch it to CSS. This year we are starting. Get perform.
Okay, page 50 in your packet. This is the last section before we start our review tomorrow. So recall that area bounded by a polar curve is 1/2 integral from A to B, or from θ1 to θ2 of r squared d theta. And r is a function of theta. Things to watch out, or things to watch for when using more than one polar curve for area is point of intersection and symmetry. We want to take advantage of symmetry because sometimes we can do less work. If we know there's symmetry, we don't have to figure out the entire area. We can just figure out a portion of the area and then multiply it by a lot of times multiply it by 2 to get the other half. So I want to show you when it says part number 1 here, find the area of the region bounded by the polar curve r equals 4 cosine theta. That's going to be this larger circle, right, with a diameter of 4, symmetric to the x-axis, and r equals 2 sine theta, which is symmetric to the y-axis. The way that we build out our area, it's a very specific way, right? We have to radiate from the origin, and it's always going to create these sector regions, right? These kind of wedges. So that's the way that we want to build it. I wanted to do a larger version of this so you kind of see all the ways. That's kind of hard to see on this diagram. So I made a larger version of it on page 51. So let's look at it from this perspective. Okay. So we know that this graph is r is equal to 4 cosine theta, right? We know this graph is r is equal to 2 sine theta. And an important thing, well, it says find the area of the region common to the polar region. So we're trying to find the area of this region. This kind of looks like a leaf in terms from previous, but it's just the common region between the two circles. Okay. An important thing is to know that intersection. Okay. So to find the intersection, we can just set the two equations equal to each other. Okay. And this one may not end up giving us a nice unit circle value, but we can just use our calculator to help us with that. So we're going to set 4 cosine theta equal to 2 sine theta.
Do we have to find the bottom intersection, or is it always going to be 0?
A lot of times, yes, a lot of times it will be 0, right? I think if not all.
Not this time, I don't think.
The bottom intersection is 0 right here, right?
Oh.
This part right here.
But when I plug in like theta, 0 for theta, it's opposite.
Not sure exactly. Well, let me do this part and then see if that helps. Okay, so if I mean, we can. I think easy way to do this. Anytime I see sine and cosine, I think in terms of a tangent here. So if I just divide by cosine and divide by 2 the other side, I can make 4 divided by 2 is 2. Sine divided by cosine is tangent. So I just figure out where is tangent equal to 0. I can use my calculator and just do inverse tangent. Sorry, inverse tangent of 2, not 0. My bad. So make sure you're in radian mode. Okay, did you guys get 1.107? Okay, so theta is 1.107. That's definitely a first quadrant because 1.107 is less than pi over 2. Pi over 2 is like around 1.5. So you know that radian wise, it's still in the first quadrant. Okay, I'm going to use a different color pen just to kind of help us see things from this perspective here. So there is a break at that intersection. And remember, if we want to do polar area, it's got to radiate from the origin. So, and it's going to fan out in a counterclockwise direction. So I'm just going to create all these. This is going to be maybe overkill once you understand the process, but for now, I'm just going to just show all these wedges that is building up. So all this time here, which graph am I hitting? Yeah, I'm hitting that 2 sine, right? So I'm going to highlight that in green here. So we can find the area of this region using just 2 sine, right? But then after we hit that intersection, what graph am I hitting after that? 4 cosine, right? So I'm going to use red to indicate that after that intersection, I'm hitting a different graph now. Highlight that in red. So this is an indication that we need 2 area formulas, one to handle the interval from 0 to 1.107, but then from 1.107 to what? Where does this end? Yeah, at pi over 2. From 1.107 to pi over 2, it's now going to hit a different graph, which is the 4 cosine theta. So if you understand the way that area works, split between 2 graphs, I think that's the hardest part. If you can see that, then the rest is just set up. Right? So then here's my area formula, split between two integrals, or equal to. Okay. So I'm going to do the green version, the green region first. So from 0 to 1.107. Again, this is hitting the 2 sine theta graph. So and then the second region is from 1.107 to pi over 2. And it's hitting the other graph, right? It's hitting that 4 cosine theta. And then the rest is just calculator. Again, you don't have to be in radian form to, in polar form to get this. You just have to be able to, plug in the calculator. You can be in rectangular form, replace theta with x if you wanted to in the calculator. So something else that I want to point out to you is that a lot of these problems, some of these problems have the graph drawn out for you, but on the test, I'm not going to draw the graph for you. You got to do it with your calculator. Same thing on the AP exam. A lot of times, if it's asking for polar area, it may not draw the graph for you. So I want us to get in the habit of it. Now, on the reviews, I do have the graph drawn for you, but I want us, as soon as we do it with the graph, I want you to do it without the graph. I want you to create the graph yourself and see if you can, doesn't have to be, you're drawing it freehand, so it can't be super accurate, but at least it's good enough, hopefully, where you can build out the regions enough to know where your intersection is, to know, but obviously you get to use your calculator.
It's gonna appear in the AP exam, is this gonna appear in the non-calculator section at all, or?
No, polar area will, I would say, yeah, I haven't seen anything with non-calculator, it's all calculator. But the only thing is sometimes they may not give you the graph, and I want us to make sure we can do it without the graph, where you can form the graph yourself with the calculator. Okay, so we plug this in the calculator and we should get 0.9617.
That's the angle. So for the second bound, I mean, the bound of the second integral, we
Yeah.
just assumed it's pi over 2, right? Because we have like a coordinate system.
Well, because I know that this is, we're talking about the 4 cosine theta, right? We know that 4 cosine theta is going to complete its cycle. It's a circle, so it's a complete cycle by pi. So that means the halfway point must be pi over 2. We can also confirm too, right? Set 4 cosine theta equal to 0. It's going to be 0 at pi. So yeah, so we can always confirm. We never have to guess. We can always confirm with setting the equation equal to whatever point that we're expecting.
So do I round to 4 decimal places or 3?
Right. So I would, yeah, 3 is acceptable. 3 or 4 is acceptable. So you can do 0.961. You can do 0.962. Okay. Any questions so far? All right. Let's go to number 2. Okay, find the area of the common region to the polar graphs. R equals 2. R equals 2 is my circle. That has a radius of 2. And the 2 minus 2 sine theta, that's my cardioid that is symmetric about the y-axis there. So the common region is, I'm gonna do this lightly, but now, first thing is I see that, well, there's symmetry here, right? So what if I just find the region in the first and fourth quadrant, or you can find the region between the second and third quadrant, and then just double your answer, right? But we do know that we have multiple graphs that are hit along the way. So I'm gonna use 2 colors here to indicate what they could be. So if I start down here, if I build my region, up until this point, I'm going to hit a certain graph, but then after 0, it's going to now hit a different graph, right? I'll do a different color there. All right, maybe I should use like red or something. So then from here to here, it's hitting the circle, and then from here to here, it's hitting the cardioid. So there's multiple ways to do this. I'm going to just try to make it all one connected thing. So we know that this circle is going to keep completing its cycle between 0 and pi. But if we look at the previous cycle, it would have completed this whole thing from negative pi to 0. And so we can think of this as the region from negative pi to, or negative pi over 2 to 0, right? If you want to go from 3 pi over 2 to 2 pi, and then jump from 0 to pi for the second interval, that's fine as well. I'm just going to make it one continuous interval here. So the first region, I'm going to take care of that fourth quadrant but to the left of 0. So I'm just going to do half the region here. So the depth integral from negative pi over 2 to 0 will hit this region. And we're talking about the circle here, so r squared d theta. And then from 0 to pi over 2, it's going to hit this upper bump from the cardioid. And then this is only half the region, so I can take this and multiply by 2. Or let's say you want to do the second and third quadrant, that's fine as well. You can do 1/2 integral from pi over 2 to pi of the cardioid. And then from pi to 3 pi over 2 of the circle. Okay, so a lot of times you have multiple ways to do it. It's just up to you. Or if you want to split up and say, okay, I want to do 3 pi over 2 to 2 pi for this region, and then jump from 0 to pi over 2 for the second region. That's fine as well. You can test all those variations just to confirm that it does work, but there's more than one way to do this.
Last time we had to set it equal, like the R's, but now like this time no. So like when do I know?
I think if it's easy to spot, you don't have to. But yeah, you're right. We could just always set them equal to each other just to get confirmation. So if I do 2 is equal to 2 minus sine theta, I get sine theta is equal to 0. So theta is equal to 0 and pi. That makes sense because 0 and pi is the intersection between the circle and the cardioid.
What about 2 pi?
Yeah, 2 pi. That's one cycle over, but 2 pi is the same thing as 0, right? It's the same. It's just a coterminal angle. Yeah. Yeah. If something lands on the axis and it's obvious, I don't set them equal to each other. But like for number 3, I definitely want to do some more work, right? I don't know just by looking at something, if it's not on the axis, what that intersection could be. Okay, good. Any other questions with 2? All right, number 3, find the area of the region common to the 2 polar curves. So we have a circle with that -6 cosine theta that's being reflected into the second and third quadrant, and then the 2 minus 2 cosine theta to cardioid that's symmetric about the x-axis, and it's that -2 cosine theta is pushing it to the left as well. Okay, so I want to take advantage of symmetry. Well, first off, let me just shade really lightly what we're talking about here. We're talking about this shaded region, right? Kind of looks like an oval. Some parts of it is made up by the circle. Another part of it is made up by the cardioid. So I like to take advantage of symmetry. If I can just figure out what this upper region is, I can just double that area and then I'll get to that bottom area as well. So I'm just going to focus my attention first on, let's find that intersection between where the graph is suddenly going to change involving the polar area. I would always try to figure out if you can solve it by hand first. If you solve it by hand, then you can get a more accurate theta value. And if you if it ends up being where it's not a unit circle value, then I would resort to using a calculator to get a decimal version. Mhm. I got 2 pi over 3 and 4 pi over 3. These are the two intersections, but I'm just going to use 2 pi over 3 because I feel like that's enough for me to get to half of the area that I need. Okay, again, I'll use 2. Let me indicate where it's going to change. So I know that my first interval is going to be from pi over 2 to 2 pi over 3. And then after that, it's going to switch to a different graph from 2 pi over 3 to pi. So the first region is going to be hitting the cardioid. And then after that 2 pi over 3, I'm sorry, it's going to start off hitting the circle first. And then it's going to switch over to the cardioid in the second portion. And I'm reminding myself that after all this is done, I only have half the region that I need, but I can just use symmetry to get the other half. So I'm doubling the area here, and that will give me the full area that I need.
I still bottom bound on the first integral, pi over. I can't read that.
Oh, my bad. It should be, because. Oh, wait.
Oh, wait, I think I get it. Oh, okay, wait, I get it.
Wait a second. Let me look.
It's because you like started from.
-6 cosine theta.
Yeah.
It's gonna be proper too.
It's a thing that's on zero to
Like that too. It should be like. Higher than two, but two higher than three.
Yeah.
Yes, that's what it looks like. It starts from zero. Yeah, that's not it. Yeah, it's. But that's the higher to the higher.
0 start at -6. Okay, so the circle is it's being drawn a little differently. Because if I do R is equal to -6. So 0 is at -6, so the circle starts here,
Oh,
right? It's a little, because it's a little bit different because of the -6 cosine theta. And then at pi over 2 is gonna be at 0. So the circle is not going to hit this point until pi over 2. And then from pi over 2 to 2 pi over 3 is where that circle is gonna hit. And then it completes its cycle up to pi over here.
So if it was sine graph, it would start at 0.
Yes, right, right. Yeah, so that feels a little bit tricky, right? Because it feels like, oh, we should be starting at 0, but the -6 cosine theta is starting at a different place, so it doesn't start our region until pi over 2. Yes, yeah. And also, this 2 pi over 3 is kind of a hint, right? This is in that second quadrant, and this is not a whole lot, so kind of makes sense that it's just from pi over 2 to 2 pi over 3, not from 0 to 2 pi over 3. So that's also a hint of that. Yeah, good question. Anything else?
Then how does it like skip to 2 pi over 3 when starting the second integral?
Okay, so starting the second interval, we know that let's see, the 2 minus cosine theta starts 2 minus 2 cosine theta.
I mean, never mind. I think I understand it.
Okay, I gotta make sure myself.
It's like one time. It's weird.
Okay. Yeah, so for the cardioid, the cardioid starts here. It hits pi over 2, and then 2 pi over 3, and then pi, and then finishes off at 2 pi. Yeah, so the fact that they're both starting at different locations kind of adds to the complexity a little bit. Yeah. Okay, you guys can copy down the bottom portion here. It says area bounded by 2 polar curves. If I want to find the area that is left over between 2 polar curves, let's say this was R1 and this is R2, then the full region from 0 to pi from A to B of R squared. And then I can subtract out the R squared to get us that middle region there. So for instance, this first integral will get us this full area. And then the second integral will subtract out this inner portion. And then what we're left with is this outer portion. Okay, page 52, number 4. So this, I'm just going to focus on the this upper portion because I know I can get that bottom portion through symmetry. So if I want to find this shaded region, I got to do some subtraction here. So the idea is that I'm going to first find the area of the quarter circle, and then I'll subtract out the portion from the cardioid, and then what remains is this outer portion here. So from 0 to power 2, I'm just going to focus on getting this full region here. And then after that, I'm going to subtract out the cardioid portion that I don't want as part of my answer. And then what remains is that shaded region in the first quadrant. Sorry, minus. All right, let's do one more. Let's do practice problem number 1. Find the area of the common interior of the polar graphs of 4 sine 2 theta and r equals 2. So we have a rose curve with 4 leaves, or 4 leaves, and then we have a circle.
The intersect feature, right? Or do I have set it equal?
Yeah, use the intersect feature. We can set it equal and use values that work. Yeah, I think unit circle can also help get us there. But yeah, that's fine. You can do intersection as well. But I'm going to do it by hand here. So I'm just going to focus on the first quadrant here. So here's the strategy. The strategy is we got to think of this as 3 separate regions. We need to find the area from 0 to this first intersection for the rose curve. And then from this intersection to this intersection will be the circle sector region. And then from this intersection to wherever the rose curve hits is going to be that last portion. And then after we find the area of this, we'll multiply it by 4 because we have 4 regions in each quadrant to worry about. So I found the intersection by hand because sine of 2 theta equals 1/2. Inverse sine of 1/2 is manageable, and then just divide by 2. Okay, so your homework is to finish off the rest of the 9.4C classwork problems, and also the 9.4 AP practice 1 through 5. So check your calendar here. Okay, so 9.4 packet, and then 9.4 AP practice as well. All right, come get your phones.
You know, here.
Is it also possible to find the quarter circle and then subtract for the community integrate?
That feels a little, I don't know, if we do the quarter circle, if we subtract. I feel like we're missing something here because these regions is different than this region. Right, because this is hitting with a different curve than this. And this as well, so it's cleaner just to look at every section. Yeah.
What are we using? Yeah. That's the part of, so from here to higher to.
The balance.
One is easy.
It's.
Yeah, we get it. So I told.
Why?
I feel fine.
No,
No, I just put it down like a media center, because I thought it was like media.
Yeah. It's like. That's how it's like scans.
I mean, I'm gonna go put it back in.
So.
No. I mean, I don't know, I saw it, it was like, it was like 10 PM I saw it. I don't know. Red chair, that one.
This one is 100 words.
Sorry, finish.
Oh, what?
Y'all got second place.
Oh, yeah.
You still want to?
I think a lot of
Okay.
Oh, yeah, yeah.
Like.
Good job, Mark.
Like.
Probably gonna change it. The pressure helps that like.
Or like.
So. We can do the. One of these extra drills. Not
Yeah, so this one here is now big stack. I'm going to our data.
Downloading it, changing it like that. I'll just say. It's gonna stand there. I'm trying to measure. Yeah, the big scale stuff. No, no.
I guess accurate, but.
This the side country like.
Yeah.
No, I think it's zero, the next zero.
Yeah. 0 to 5 which we. Minus.
I think
If one was intersecting angles, so would you. And then if the.
Yeah, it's like the thing. I can do the calculator.
Sometimes it looks like zero, but it's actually higher than two. You can't do that.
How do I know? Is there one thing like negative?
What?
How do I know? Is there one thing like trig negative?
Plug in zero for theta and then where the starting. And then like I think you know.
Okay.
Because
So.
I don't fully understand how. Have a good day.
Good day, thank you. All right, good day. Just.
I don't know. I didn't believe.